Hello friends, welcome you all. So in this video, we will discuss the conversion of finite automata to RLG. RLG is right linear grammar. So as you know friends, we have in finite automata, we have transitions and we have states, then we have input symbols, and in RLG, we have variables, we have terminals and production rules. So how we will do this conversion, that we will discuss now. So first of all, I will tell you some rules regarding this, and then we will discuss any example finite automata to convert into RLG. So I will start with rules. So suppose in particular finite automata, if you have two states and you have any input symbol x between them, so this may be one production in your finite automata. So how you would convert it into equivalent production rules? So I can write it as a gives xb. Now one more condition you may have there, like you have two states again and you have one more input symbol x there between them, and now this time b is final state. So in this case you would write when like you can write it like a gives xb, and you will add one more production here, a gives x, as b is final state, and as the transition of x from a is reaching to final state, so you will add one more production here, a gives x. Now one more condition may be there. Suppose your final state, initial state is also the final state, so in that case you need to add a gives epsilon, a gives epsilon. So these all these rules you will apply when you are converting any finite automata into RLG or linear grammar. So now I will take one example finite automata here, and then we will convert this particular finite automata into RLG. So now friends, we have this particular finite automata as an example, and now we will convert this finite automata into equivalent RLG. So now first we will consider initial state. So as initial state is a here, so we will create that particular variable, and this will be the start symbol of the grammar. So we can convert the transition of a into equivalent production rules. So on a, if we are applying b, sorry 0, so we are having we are moving to b, so I can write a gives 0b. And on a, if we are applying 1, so we are staying on a, so I can add one more production there, a gives 1a. Now both the transition of a we have considered, so now we will consider the transition of b. So now on b, if we are applying 0, so we are moving to c, so I can write 0c, but c is again final state also, so I can write 0 also. And on b, if we are applying 1, so we are moving to a, so I can write b gives 1a. So these three productions will be added for b. Now for c, if we are considering c here, so on c, if we are applying 0, so we are moving to b, so I can write c gives 0b. And on c, if we are applying 1, so we are moving to, we are staying on c itself, so I can write 1c. And as c is final state also, so I can write c gives 1. Now these are the production rules that according to this finite automata we have considered and we have created. Now we will check whether any particular variable or productions are useless or not. So if you can have any production rule, any variable which is there in the right hand side of production rules, but no product transitions are there for, no production rules are there for that particular variable, so you will consider this as useless variable, and you can remove this. So in this particular grammar, you can see all productions are there, and we have three variables in this grammar, and the a is a start variable, b is another variable, and c is another variable, And for A, we have two productions. We have for B, we have three productions. For C, we have three productions again. And this is the equivalent grammar for that particular finite automata. So this is how you can convert any finite automata into RLG. I hope this would be very much clear. I will take another example now and I will tell you how to convert that particular finite automata into RLG. So now friends, this is one more example where we have four states. D here is final state. So now we will convert this particular finite automata into RLG. So now we are considering first A. So for this is one NFA. If you can observe, it is NFA. So we will now apply all these rules on this particular finite automata. So on A, if we are applying 0, we are moving to D. And as it is final state, so I can add one more production here. A gives 0. Now on A, if we are applying 1, so we are moving to B. So I can write 1B. Now on B, if we are applying 0, and there is no transition of 0 for B. So if on B, if we are applying 1, so we can stay on 1 or we can move to C. So I can write 1B and 1C. Now on C, there is no transition of 1 on C, but on C, if we are applying 0, so we are moving to D. So I can write for C, I can write 0D, and as it is final state also, so I can write 0 itself. Now as a D, on a D, we have no outgoing transition for 0 or 1. So we will not write any production for D. Now in this particular conversion, if you can see, according to the rules, we have created all the production. Now in this particular grammar, you can see D is appearing only in the right hand side of production, but we have no production for D. So D you can consider as useless symbol, and all production where you are having a D you can simply remove. So if I remove this production and this production, so this grammar will become like this. Now, so after removing useless variable D, the grammar becomes like this. Now again, if you can further reduce this grammar, then we can try this possibility also. So now you can see we are having one production of C, and also we are having only one production where C is at right hand side. So if we replace this C with its production, then we can remove this production also. So what we can do, we can replace this production, we can replace this C with its production, and we can create one more production. We can remove this production and we can create one production like B gives 1 0. B gives 1 0. So in that case, we can simply remove this production also. So for this particular finite automata, the final grammar would be A gives 1B and 0, and B gives 1B and 0. Sorry, 1 0. 1 0. So this would be the final grammar for this particular finite automata. So I hope this would be very much clear, as this conversion is very much useful when you are converting any RLG to LLG or LLG to RLG. So this particular conversion is very much useful there. So now we will see how to convert particular RLG to LLG or LLG to RLG. So friends, now we will discuss RLG to LLG conversion and reverse conversion LLG to RLG. For both these conversion, the conversion of finite automata into RLG is necessary. So we have already discussed this conversion. Now I will tell you the process of converting any RLG to LLG and any LLG to RLG. Then you can convert easily. So now very important thing is there, like if your RLG is generating language L, so when you are converting it into equivalent LLG, so this LLG must also generate language L. So this conversion, how to do this conversion, this we will see. So now you can see here how to convert any RLG to LLG. So I am first discussing RLG to LLG conversion. Now RLG, from RLG you can convert it into finite automata. RLG, you can convert it into finite automata. Suppose this particular RLG is generating language L. Then this finite automata will also accept language L. Then this particular finite automata you will convert into finite automata A dash, which is accepting language reversal of L. How would you convert this particular finite automata to accept reversal of language? So you can interchange initial and final state, and you can reverse the direction of each transition in this particular finite automata. So you will get reversed finite automata, or I must write here reversed finite automata. So now this finite automata you will convert into reverse finite automata, so that this reverse finite automata will accept reversal of L. If this finite automata is accepting language L, then reverse finite automata will accept reversal of L. So now this, then you will convert this reverse finite automata into equivalent RLG, that we have discussed the process, equivalent RLG. So this particular RLG will generate reversal of L. Then by reversing right hand side of each production, you will make LLG. So this will accept language L. This will generate language L. So you can see, if your RLG was generating language L, so by all these conversions, you have converted it to LLG, which is also generating language L. So this is the process to convert any RLG to equivalent LLG. Now we will see the reverse conversion. If your LLG is generating language L, then you will convert it to RLG by reversing the right hand side of each production, so which will accept reversal of L. Then you will convert this RLG to FA, which will again accept language reversal of L. Then you will convert this FA into reversed FA. So this reversed FA will accept language L. Now you convert this reversed FA to RLG. So if your reversed FA is accepting L, so this RLG will also generate L. So this is how you can convert any given LLG to equivalent RLG. So this is the process of converting RLG to LLG or LLG to RLG. So I hope, friend, it would be clear. Now I will take one example of both, and then we will see step by step how to perform this conversion. So now, friends, this is one example RLG that we will convert into equivalent LLG. So now we will start, we convert any RLG to LLG in 4 steps. First step, then second step, then third step, and then fourth step. So we will perform all these conversions one by one. So suppose this is your given RLG, and now we will convert it into finite automata. So I will take one, this particular RLG is having only one variable, and it is having 3 productions of S. So I will create one state here S, which is our initial state, and then I will create both the transition corresponding to all these productions. So on S, if we are applying 0, so we are moving to the S itself. Then on S, if we are applying 1, so we are moving to 1 S itself. And then we are having also one more production, S gives 0. So as it is only terminal, so it must lead to the final state. So I will create one final state here, and I will create one transition of 0 from S to F. Now this is the starting this is the corresponding finite automata equivalent to this RLG. Now I need to convert I need to reverse this finite automata so that it will accept the reversal of language. So now you can, how you can convert this to accept reversal of language. So you just interchange the final and initial state, and also the direction of each transition. So as in this particular finite automata, we are having only two states. So one is initial state and one is final state. So I will exchange these two states now. So I will write S as final state, and I will write F as initial state. Now, as S is F is initial state and S is final state, so we will reverse the direction of transitions also. So I can have, after reversing the transition of these two transition, direction of these two transition, again it will go to the same state. So I can write like this. Now this particular finite automata will accept the reversal of L. Now we will convert this particular finite automata to RLG. So I will now convert this particular finite automata to RLG. So how you can do it? So first we will consider F as it is final state. So on F, if we are applying a 0, so we are moving to S. So I can write like this. Now on, there is only one transition for state F. Now on S, if we are moving, if we are having applying 0, so we are moving to S itself. Now as S is also the final state, so I can write 0 again. S gives 0, and on S, if we are applying 1, so I can write, we are staying on S itself, so I can write S gives 1 S. But S is also the final state, so I have to add one more production there. S gives 1. So now this is the equivalent grammar which is generating the same language accepted by this finite automata. So now this is RLG. Now we can convert this particular RLG into LLG just by reversing the right hand side of production. So I can have F gives SO. I can reverse the direction, and then S gives SO, S0, then S1, then 0 and 1. So this would be the equivalent LLG to generate the same language generated by this grammar. So here in this particular grammar, we are having only one variable, while in this particular grammar, we are having two uh, in this in the given RLG, we had only one variable, and in the equivalent LLG that we have got, so we have in this particular grammar, we have two variables, and this is the final LLG equivalent to this RLG. So this is how you can convert any RLG to LLG. Now I will take one example of reverse conversion like LLG to RLG. And in this particular example, I will use some different types of grammar. So friends, now we will see the reverse conversion here, LLG to RLG. Now it is again 4-step process. So this is first step, this is second step, this is third step, and this is fourth step. So these 4 steps we will perform one by one. So first we will convert this LLG to reverse RLG so that it will accept generate reversal of L. So suppose this particular LLG is generating a language L, then we are performing first conversion here. So reverse LLG RLG would be 10A. We will reverse the right hand side of each production. So we will write 10A, then A gives 1S, and this is after reversing again it will be 0. So now this particular RLG will generate reversal of L. Now we will perform the second conversion here. So we are writing second conversion here now. So we are converting this particular RLG to FA. So we are having two states, two variables here. So we will now create two states here, S and A. So as you can see, my friend, here we have two states here. Now this is our initial state, as S is our starting variable, start symbol of the grammar. So now on S, if we are applying 10, so we are moving to A, 10, and we are moving to A. And then on A, if we are applying 1, so we are moving to S again. And on A, if we are applying a 0, so we are moving to final state. So I have to create one more state here as a final state. And this is 0 transition for A. Now you can see here, we are having here 10. So we cannot have two symbols at one transition. So we will divide this particular transition into two stages. So I will add one more state here, which is B, and I can write 1, and here it would be 0. So total 10 transition would be there. Now you can see this is our final state. We have considered all the production here. We have considered all productions of this reverse RLG, and we have created this finite automata for this particular RLG. See, as this particular grammar is generating reversal of L, so this finite automata will also accept reversal of L. Now we need to reverse this finite automata so that it will accept the language L. So now how to reverse that particular finite automata? So we will interchange the final state and initial state, and reverse the direction of all transitions. So I can create it like this: S, then E, then F. So now one more state is there. Very sorry, one more state is there between S and A. So I can write B and then A, then F here. So now here F is final state, S is initial state. So now S is initial state, so I will make it final. F is final state, so I will make it initial state. And I will reverse the direction of all transitions. So on 0 transition, we are moving here. Then on 0 transition, we are moving here. Then on 1 transition, we are moving here. Then on 1 transition, we are moving here. Now this particular finite automata will accept the language L. Now, as it is accepting the language L, so if we convert that particular finite automata into RLG, then this RLG will also generate L. So now, this is the third transition, third step. Now we will perform the fourth step of this process, which is conversion of reverse FA to RLG. So this is our reversed FA. So we will convert this reversed FA to RLG. So we will start from initial state F here. So F is our initial state. So I can write equivalent production rules for this state. So on F, we are applying 0, so we are moving to A. So I can write F gives 0 A. Then we will now convert all transition of A to production rules. So on A, we are applying 0, so we are moving to B. So I can write A gives 0 B. Now on B, we have one more transition there. On B, if we are applying 1, so we are moving to S. So I can write B gives 1 S. Now, as S is final state, so I need to add one more production here. B gives 1. And then the production of S, I can write as S gives 1A. S gives 1A. So this is the grammar that we have got after converting this particular grammar from LLG to RLG. Now, the language of this grammar is L, so the language of this grammar will also be L. As we have found this grammar from this finite automata, and this finite automata is accepting language L. So this grammar will also generate language L. So when you convert any LLG to RLG or RLG to LLG, you may have some useless variables and useless productions. So you can simplify this grammar. This is the process of converting any LLG to RLG, and I hope this process is very much clear to all of you now. Now, if you have any doubt, you can always write to me in comments. I will definitely reply your comments. Thank you so much.